constructions is already underway. And as I try to explain, energy is not the issue. Energy must always be conserved. The issue is the rate of entropy reduction. And to keep that entropy balance in check. And so, using photosynthesis, historically that has been the case, but it seems that due to human action, the production of entropy, because of this very low energy efficiency, so we need a tremendous energy input, which essentially to almost 100% is then converted into heat. So it's heating up the environment, contributing to the increase of entropy. So that balance is not given anymore. And of course, in this context, energy use, inefficiency of energy use, those fossil fuels that are being burned produce carbon dioxide. And carbon dioxide has been identified as one of the problems that also causes the climate change. But in my view, that could be a misleading discussion. Because, well, it's sort of maybe misleading in the sense that it suggests there could be a technological fix. We may be able to come up with technologies to store carbon dioxide and so on, get it out of the atmosphere. Again, so to, let's say, reduce the carbon dioxide level to what it was in pre-industrial times. Maybe by technological fixes that is possible. But actually, it does not solve these fundamental challenges. They may still be around, and they may be actually much more severe and daunting than the carbon dioxide problem. And there is no simple technological fix for this. So, like the increasing power demand, which is related to population growth and so on, the finite resources, all of these issues have nothing to do with the carbon dioxide problem. And this is something, well, a simple calculation based on thermodynamics that I suggest. So, and something that everyone can do. So, the energy consumption rate is currently about 15 terawatts. Now, one can use a famous theorem of thermodynamics, the equipetition theorem, and, well, calculate a corresponding temperature change per year corresponding to this energy consumption rate. And now the result of this will give you climate change just based on thermal effects, having nothing to do with carbon dioxide in the atmosphere. And I think it's an interesting exercise for two reasons. One is, well, you will see what the main issue with all climate models is. They're extremely complicated and they involve a huge number of degrees of freedom. And so there will always be a level of inaccuracy just because we are dealing with these large numbers. And well, the other interesting result is it's based on well, parameters that I use. And I encourage well, you to do your own calculation because it's really simple. Based on parameters that I use, I came up with a result that lies in the range of something between 100th and 1/10th of a degree per year. And so that would be quite significant, a quite significant contributor to climate change, actually. Having nothing to do with carbon dioxide in the atmosphere, just by releasing heat, by heating a pot into your kitchen, and it's of course warming up. And the amount or this energy consumption rate may be so high that this effect could be quite significant. But then also you will realize these assumptions are really critical and they are like mind-boggling. So it's, what do you assume about energy exchange between atmosphere, oceans, and so on? All of this, right?
What about this energy can be radiated away, right? Can be radiated out of the system.
Sure. Of course, it's an open system.
Yeah, and if you take it into account, depending on the rate, if you could make a combustion, you can actually increase the temperature if you radiate more than 50%.
Absolutely. So so it could give you like a very simplistic and extreme scenario. And of course, it doesn't account for any of the coupling of the couplings. But reinforces my belief that global temperature increase has an anthropogenic origin. And it's not necessarily coupled to carbon dioxide. So there is not necessarily a simple technical fix for the problem. It requires fundamental societal changes, actually. We have to address the issue of this dramatic inefficiency of energy use that we are accustomed to. And so there are things that can be done about it, or that in principle must be done. We have to reduce this inefficient use, we have to exploit abundant sources, we have to get away from those sources which are like declining. And these are societal issues, so it requires social political stewardship to provide incentives to reduce this inefficient energy use. But so what science can contribute to is to develop efficient technologies that increase for the actions, for our daily activities that we have to perform, make them more efficient, so that we can perform the same actions but with less energy. And so this, in my view, establishes the case for electrochemistry. And so in the remainder of my talk, I will talk a little bit about that. So energy technologies have to be evaluated by their efficiency. That's the main factor. Then, of course, abundance of resources to power energy technologies, which fuels are needed as input, how readily available are they. But it's also a question of how readily available and how cheap and abundant are the materials that we need to fabricate batteries, fuel cells, and so on. And then there are certain infrastructure needs, for instance, in the case of polymer fuel cells or fuel cell, other types of fuel cells. It's a question of the fueling infrastructure, and hydrogen is the best fuel to power a polymer fuel cell with. So it's a question of will there be a rapid enough development of a hydrogen fueling infrastructure. And so all of these factors have to be taken into account. Certain characteristics of electrochemical energy converter and storage are. These technologies are very diverse. They encompass photoelectrochemistry, batteries, fuel cells, supercapacitors, many more. And they're compatible as well with conventional as well as renewable sources of energy. And well, generally, and this is of course of interest for us, doing the scientific work, we're dealing with the complex materials and phenomena. And so this is a slide comparing the incumbent technology, which is based on steam engines, combustion engines, and limited by no efficiencies, which can be calculated, predicted to, or known to produce atmospheric pollution. On the other hand, electrochemical energy conversion directly converts chemical energy stored in a fuel into electricity. Electrochemical technologies are unrivaled in terms of efficiency. They can be much more efficient than steam engines. And they are silent, and if operated with the right fuels, they produce no pollution. And so this is paraphrase from the publication that I found. It's actually quite a famous publication, and the author also predicted that practical realization would take a long time. And the interesting thing about this is, so these are all my commonplaces more or less, but the interesting thing about this is that it was published in, as you see here, 1894. The author was William Oswald. And so more than 100 years ago, he was predicting this. So this is, well, our statements made by a true visionary of his time. And in principle now, we are much closer to actually the practical realization. So what is electrochemistry? We can define it as in various ways. It's a branch of thermodynamics. So, well, to conventional thermodynamics, we have to add one more state variable, which is the electrostatic potential phase. You can also define it through the materials or systems that we are considering. Usually it's heterogeneous systems which have interfaces between metal electrodes and electrolytes, which could either be liquid electrolytes or solid state electrolytes. And there's also a process-based definition that electrochemical processes always involve the separation of electrons from a reactant. And the electrons are forced on an external pathway through metal wiring. They can perform work. And electrons can be stored intermittently. And this is what happens in a capacitor or batteries, rechargeable batteries. Or they can be part of a continuous process. And so continuous electron transfer and recombination with ions. This is what happens in fuel cell or pellet cell batteries. And so a few simple pictures on what is an electrochemical system. So a glass of water is already an electrochemical system. We can measure the capacitance of water as an interesting dielectric spectrum actually. Now we add ions to the water. I mean usually tap water contains ions. So it's a liquid electrolyte. One can apply again the potential, an electrical potential, and study ion transport, characterize the electrolyte by its ionic conductivity. You can go further and now dip a metal stripe into that electrolyte, and there will be interesting processes occurring at that metal stripe. Some of the ions or some of the metal atoms will go into solution and become ionized. And so what we'll establish is this so-called electrochemical interface. And this is an interfacial region between the surface of the metal and the electrolyte with a thickness in the range of a few angstroms, so very small, 10 to minus 10 meters or a few nanometers. And in this region we get huge electrical fields and potential distributions which control ion distribution, as well as the processes at the interface. Now, next, one can take two different metals, put them in the same electrolyte but in separate vessels, and connect them by a metal wire. And usually what one will observe is that there will be a current flowing and there will be a potential difference between the two. And then the current will be decaying, and in the end of the process the potential difference will be balanced out. And so this is just a thermodynamic approach to equilibrium that happens. So these are spontaneous processes that occur. Redistribution of electronic charge. So that's a typical electrochemical system. This is in principle what happens in a battery. And so usually, we are dealing with these interfaces, processes occur at these interfaces. So total interfacial area is a key parameter. The larger that interfacial area is that can be packed in a certain given volume, the higher will be the power density and energy density. So from a technological perspective, that is very important. And in order to get these high interfacial areas per unit volume, we are generally dealing with nanoscopic materials, nanostructured, or random heterogeneous media. So I think I have about 5 more minutes or something like that. So one can compare then different electrochemical energy conversion and storage technologies. So the known ones are capacitors, batteries, fuel cells. Here compared with the combustion engines, which are highly developed, and they have high specific power density, so high power or amount of energy that can be rapidly released per unit volume or per mass of a device, as well as a high specific energy density. So this is the power density is important in terms of the dynamics. So for automobile, that translates into the kilowatt number. And well, the specific energy density is important for the range. So there's a certain advantage that fuel cells have over batteries. Usually they have significantly higher energy densities. And so nowadays fuel cells with the same volume of a device can provide provide ranges in the range of, I don't know, 500, 600 kilometers with one filling in a fuel cell vehicle, whereas batteries are severely limited in terms of the range. And there's even something that is called limited range anxiety that the developers of battery electric vehicles have to deal with. So customers fear buying or using battery electric vehicles because it's very difficult actually to predict what is the range that one can go with a single charge of the battery. Strongly dependent on the rate at which the battery has been charged and so on. And but I mean, these automotive applications are not the only ones for fuel cells. So this shows first of all the scaling or the range of power output of a fuel cell device. So they span a wide range, and going from power needs of small portable devices, laptops, cell phones, and so on, to mobile applications, including automobiles, as well as buses, heavy-duty mobile applications, as well as larger installations for stationary power supply in remote regions and so on. And so, what is the blueprint for electrochemistry, and why is electrochemical energy conversion so efficient? It's very close actually to biological energy conversion. So there are certain similarities. I will not go into all of these details because these are complicated topics. But basically what happens, so when solar energy hits a plant or an electrochemical device or photovoltaic device, is charge separation is occurring. Basically, electrons are separated from either water or metal atoms. So charge separation takes place. And then these charges can be stored either directly in, for instance, capacitors, or they can be converted or used to produce liquid fuels. And this is what happens in electrolysis. Basically, the light of the sun is used to produce a fuel, to store either electrical charge or to produce a fuel that then can be stored as a liquid fuel. And so photosynthesis, as I said before, has an efficiency less than 1%. Nowadays, commercial photovoltaic materials have efficiencies of about 18%. And there are some materials tested at the laboratory scale which even have efficiencies up to 40% photovoltaic efficiencies. So they can harvest the light of the sun much more efficiently than what occurs with photosynthesis. This, in principle, it's an argument against biofuels. And again, if you were here last week for the presentation of Peter Burke, he was discussing that energy return on investment, something like that, which was very poor for biofuels. Basically, the reason for that is that harvesting factor for the light of sun in photosynthesis is very poor. And photovoltaic devices, photoelectrochemical devices, can have much higher efficiencies. They can harvest the light of the sun much more efficiently. And then if you use the electrons generated in these processes to produce, for instance, hydrogen, one has to multiply that efficiency with the efficiency of electrolysis, which is about 70%, and so we get an efficiency of hydrogen production of about 12%. So significantly better than the efficiency of photosynthetic production of liquid fuels. Then the reverse processes are shown here: recombination of the fuel with oxygen, aerobic respiration, or what happens in the fuel cell if hydrogen and oxygen produce water. So respiration has efficiencies of up to 90% in some organisms, and the efficiencies of fuel cells are nowadays in the range of 60%. It's actually not far away. There are some significant differences, of course, biological systems, the charge separation that occurs. Sun of light is used to separate electronic charge from nuclei, from molecules. Occurs over microscopic distances. And also, well, as one can easily estimate, the power density of biological organisms, so the rates at which these processes occur, are much lower by many orders of magnitude than the rates at which we need them to occur in these technological devices. So roughly a fuel cell must have about 1,000, maybe even 10,000 times higher rate for a given volume than a biological organism. And that is the reason why in respiration, the biological system is much more efficient than the electrochemical system. And so just running through considerations of efficiency. So why is the efficiency of the electrochemical energy conversion so high? So this would be the direct reaction of hydrogen with oxygen to produce water, direct combustion, has a certain energy associated with it. Now, we take the same reactants, but we split them spatially. So one reactant we have in one compartment, another reactant we have in another compartment, and we conduct the same reaction. Now, in order to complete that reaction, we first must strive for the electrons here from the hydrogen. Leave the hydrogen atoms as protons. Electrons go in one path, protons go in a separate path. And again, now these electrons and hydrogen recombine with the oxygen to form water here. So the net reaction is the same, but we have split it up and separated it spatially. And now, thermodynamics gives us a value of the maximal theoretical work that can be used from this reaction, and that is, gives free energy. And there's a certain amount of heat or energy associated with entropy gain that is released in this reaction, and that is given here. And so then we can calculate the reversible thermodynamic efficiency. And so this is the reversible work that can be conducted. Of course, this reversible work, accessing this work requires that the process has to be extremely slow. If we want to run it at higher rates, not get high power densities, energy densities, and so on, we have to increase current density. And so these current densities are flowing through all the components in the system, through the catalyst material and metal electrodes, through the electrolyte and so on, and at interfaces. And so there are certain losses, irreversible losses of energy associated with all of these processes. The higher the current density is, the more of the energy of the reaction we will lose.